Yeah, well, I hope everyone is able to hear me and understand what I'm saying. But yeah, this should be recorded. It's going to be a long recording, I guess. So I hope everything goes okay with that. But okay, I see we have quite a bit of new people here. So maybe we should get started. So welcome everyone to the anti-trash laboratory demonstration. You are all virtually present here in the at Aalto University campus in the warm and sunny Finland. You picked a great time to visit, and yes, as Kari mentioned, we have quite a bunch of new names here. So I think a round of or like a quick introduction is required. So my name is Risto Ojala, and I'm working as a machine vision researcher in the Anti-Trash project. The Anti-Trash project is an EIT-funded research project with the goal of developing technology for monitoring the cleanliness of public transportation vehicles and shared vehicles. And we've got partners from different parts of Europe. I don't think that I can list everyone now, but different partners with a different background in university, industry, transportation service providers, and yeah, in the end, we'll have time for questions. So if there are other introductions to be made, I think we'll have time then. So the basic schedule of this demonstration will be that I'll be demonstrating my work with machine vision in public transportation vehicles, utilizing the setup that should be visible in my other camera. Do you see another camera from me?
No.
Okay. Let's see. I had it a bit ago, but I guess it has for some reason. Okay, here we go. For some reason it has stopped presenting, but anyway, I'll be presenting my work with public transportation vehicles, and I'll be demonstrating our machine vision algorithms in this kind of development environment we built here in a laboratory at Aalto University. And yeah, this will take the first half of the demo. I'll present the algorithms, then we can have a round for questions. And after this, Nilusha will be presenting his work with shared vehicles. And similarly, after he has demonstrated his algorithms, there's good time for questions. Okay, so I guess we can start jumping right in. Oh, and by the way, if there are any questions like along the way, you can just open your microphone and ask them. I'll be able to answer them right away. No need to wait with all the questions to the end if it's like something that is currently being shown, or yeah, something related to the specific fact that I'm talking about. But okay, so regarding the setup we have here for the public transportation setup, we've constructed this. We've used these bus seats to make this kind of setup that is somewhat familiar to a bus or a tram, and we've been using this to get a basic start developing algorithms that will later on in the project be deployed in real public transportation vehicles. And the development here. So in this other camera, you can see the area, what it looks like. I'm gonna close that for a bit so that I can have your attention focused on what's behind me here, basically. So you can see that behind me is the area that I just showed in the other camera view, and here on top you can see this wooden panel where we've attached different equipment. So where I'm approximately trying to point right now, you can see these LED lights. We have been using these with we have these cold and warm lights that we've been using with different brightnesses to basically ensure that the algorithms we are developing are able to handle different lighting conditions. Or at least they provided us a multitude of different lighting conditions in the winter time. But since Finland is known to be quite sunny and bright during summertime. Now they haven't been able to give us a kind of different lighting, so the lighting is kind of constant in the setup at the moment. But yeah, in addition to lights, you can see different cameras we have installed here. I'm trying to point to them right now. This one here is a regular kind of a wide-angle camera, so that it's a stationary wide-angle camera, very similar to kind of many surveillance cameras that are available. And then this other one is a linearly actuated camera. So it is this one that looks like a very long box. It has a camera inside it, and the camera is able to move linearly along the box. We decided to try this approach to basically evaluate what kind of benefits and effects we have by being able to move the camera. So we basically get different viewpoints of the environment. We can play with different confidence and uncertainty, and overall get different kinds of results. And yeah, both of the cameras they have small Raspberry Pi computers inside of them, and these are basically perfect for development. It's the kind of thing why we are making our own cameras in the first place. So with these Raspberry Pis inside the cameras, we have a full range of internet connections for development, for future installations in public transportation vehicles, and a wide variety of different ways that we can choose when to record the environment. And yeah, I'll try to take you for a closer inspection of what the cameras look like. This is a bit difficult considering I'm not an expert cameraman, but let's see how we do. So okay, so yeah, here we can see the linear camera. Hopefully you are able to see basically the camera box inside it, and that is actuated with a belt and a linear rail. It is able to go through this whole length and capture images from different positions. And basically next to that, you can see this wide-angle camera designed by us. And yes. So again, they have small computers inside them basically that allow different that are optimal for development, and allow different types of connections, and also different types of capture protocols. Okay, so coming back here, I think that's enough about the setup. So I jumping jumping to the actual algorithm demonstrations. So what I'm gonna do next is I'm gonna show you how the algorithms work and show you the results of the algorithms. And for this, I have set up a web page. Here we go. Okay, I'm gonna share my screen now. Okay, so I have a web page here that anyone can connect to on their home computer. So if you have another screen, or you want to get a better view of the results we're going to get, I recommend you open your browser and you type this IP address in there. I've also commented this in the chat of this meeting if you want to find it. Yeah, so yeah, all the results from the cameras I'll be showcasing. They will be displayed here. If you want to see them for yourself and scroll the web page on your own, I will be showing them here as well. But yeah, that's something you can do if you want to get a closer look. But okay, explaining this web page a bit, because soon I'll start capturing images and displaying the results in here. What I've already done is that I've taken the results for the empty scene already, because I want to focus on detecting trash and detecting valuables here in the environment. So I've already taken like a clean. I've already processed the results for the clean environment. And how the results are displayed here, you can see the captured image here on the left of my screen. And then you can see this black box here that I've labeled background subtraction. This is actually the first result we'll be getting. So what happens here is that a machine vision algorithm, we have taught this machine vision algorithm what the environment is supposed to look like, or it has been self-trained. It has seen images of the clean environment before, and it has learned this probabilistic model of what the environment is supposed to look like. And here in the background subtraction box, it will be displaying everything that is not looking as it should be. It is displayed in white. But now it's just a black box because the environment is as it should be. So it's not detecting anything out of the ordinary here. And what we do here after analyzing this background, if we find any sort of objects that are not supposed to be there, we use a neural network to evaluate what the objects are. And in this case, since there were no objects to evaluate, we just say that okay, the environment is clean, and there is nothing to evaluate. And these are the results for the wide-angle camera. And in addition to these, I'll be showing the results for the linearly actuated camera. And here you can see how the camera, it has moved basically along the corridor and captured images at each step. So we have 5 steps now. More could be taken for higher confidence or further analysis, but 5 steps are used here because it is quite sufficient, and it is not like overdoing it. And for all these images, we do individually the same thing as we do for the wide-angle images. So we do background subtraction. We analyze the background that the algorithm has learned on its own beforehand, and then if we find anything out of the ordinary, we use a neural network to classify what that is. And here again, there is nothing out of ordinary, so everything is clean. And on a note, like why we are doing it like this, that we take a look at the background and then we evaluate the objects we found here. The reason is that this approach is basically very generalizable. The background subtraction, it learns on its own, so you just have to show it what the background is supposed to look like when it's clean, and it will learn what it's supposed to look like. And then if there is something out of the ordinary, we will evaluate it with a neural network that has been trained with general images from the internet. So yeah, this should be completely generalizable. Of course, there will be situations with like varying lighting and so on that the background subtraction gets distracted, but hopefully the neural network it should be able to distinguish situations like that. But okay, so this is how I'll display the results for you. So what I'm going to do now is that I'm going to go and put different objects in the background that was clean at the moment. This image is the current situation, so it is perfectly clean at the moment. So I'm going to go and put different valuables and trash objects in there, and then we'll see how the algorithm works. So yeah, I guess I'll share the other camera so you have a bit of an idea what's going on, and then you will be able to see well when I show the results from the cameras. So just half a minute, I'll go and make a mess and leave some of my personal belongings in the area behind me. Okay, so what I just did, I went ahead and I left my mobile phone there. I left a backpack and also some general food-related trash, some cans, a bottle, a coffee mug, this like one-time use coffee mug, and this kind of food bag that you can have like a bread in or whatever. Some quite typical trash you might find in a public transportation vehicle. Okay, so I'm gonna change the screen here back to the web page. Yeah, and then I'll activate the cameras. Okay, so what's happening now is that I've asked the cameras to take pictures for us, and so yes, so the cameras take pictures, and after they've taken these pictures, they transfer the images over the internet to our server in Frankfurt, Germany, and what the images are transferred over 4G. We wanted to test out these kind of mobile connections, which are often the way you handle internet connections in vehicles. And yeah, so now the images are transferred to the server, and the server does the processing. Okay, so our first results are ready for the wide-angle camera. If you are viewing the web page on your own browser, you should refresh it with Control and F5. This is necessary because otherwise the browser may not update the images. But if you press Control plus F5, you should now see these new images here. So what you see now is that all the objects are there that I went and put there. So we have a coffee mug here, and someone's left their backpack. Someone's left their mobile phone by accident, that's fallen out of their pocket, and we have these other bottles, cans, this bag, food-related trash. And now the background subtraction that I was talking about, which is probably a bit difficult to understand because it was just a black box. But now you can actually see and compare to the image right next to it. You can see that all the things that are not supposed to be in there, they're highlighted in white. And did we manage to capture every single object? Okay, this it seems like that this blue can, this one has not been detected by the background subtraction. The reason is probably that it is the side of the can is quite similar in color to the side of the mat here. So it has probably been detected for a few pixels. The algorithm has probably detected that there is something a bit funny there, but there is this some filtering going on to remove noise. So it has probably been removed because it has been such a tiny difference in the background. Okay, so we now we know which areas to process with the neural network. So let's see what the result looks like. Okay, it's looking pretty good. So here you can see that the coffee mug, with everything with this red box is trash, and everything with this blue box is evaluated as a valuable. So you can basically see here that the coffee mug, it has been correctly detected as trash. The backpack, it has correctly been detected as a valuable. So we know that there is something, someone has left something in there, and tracking what's going to happen next to it. If this was a real public transportation vehicle, we would now know that we're going to have to record this area with the surveillance cameras because we want to see what happens to the valuable forgotten object. We can also see that the mobile phone has luckily been detected as a valuable. So we've managed to get the valuables correctly evaluated here. And the rest of the trash, seems to also be correctly evaluated by the neural network. But again, this scan, it has not been detected. It's not a mistake by the neural network. It's a mistake in the background subtraction, which did not detect. It was filtered away in the results. So this scan was not fed to the neural network, and therefore this trash has gone undetected this time. But these things happen, and that is why the linear camera, which may be quite impractical in terms of installation and other practical things, but in terms of these machine vision properties, it is very useful. The results for the linear camera are ready as well. I'm going to refresh the page now. It was Control and F5 in case someone is looking at the web page on their own. And moving to the linear images, we can see that okay, these are the linear images, and we can see that all the objects are here as well. And similarly as with the wide-angle camera, all the background subtractions are here, and we can see that this time, as I said, the different points of view can help, and you can see that everything is detected here. Even the blue can, which was difficult here in the wide-angle camera, it was not detected. But here you can see that it has been correctly detected. Even here when it's only partially visible. So this is the kind of this highlights the benefits of the linear camera. And yeah, so the background subtractions seem to be okay. Everything has been all the differing portions of the image have been detected. And let's see what the neural network results look like. So everything's looking pretty good. We can see that the trash has been detected correctly. The mobile phone is detected correctly in every image, but here in the last one it is only partially visible, so it has been detected as trash. And yeah, all the trash has been correctly detected in every image. The backpack has been detected as trash here, as it's only partially visible. But again, since we have the different viewpoints brought by the linear camera, we can see that in these images it has been correctly detected, and overall we have a very promising result, as all the trash was detected and all the valuables were detected with a certain confidence. Yeah, so this was a demonstration of what the algorithm does and how the results look like. Looking at the time, I think I don't have time for like any more arrangements or changes. So these are the results, and yeah, in laboratory conditions, as you can see, the algorithm operates already very well. It is able to detect trash and valuables, and yeah, the operation is consistent in the laboratory conditions. What's coming next for this algorithm is that we are planning on camera installations in Hamburg Hochbahn in Germany, and Icarus buses in Hungary, and with those installations we'll get to see how well the algorithm is able to operate in kind of real scenarios, because the laboratory scenario is in many ways ideal. There are not that many like lighting issues and all the different things that real world kind of brings to you. So yeah, the development at the moment the results look promising, but the development will continue in real world vehicles. And yeah, I'm very excited to see how that goes and what kind of how the algorithm operates there, and what we have to change and fine tune to make it even better in the real conditions. But Yeah, considering I've already used half of the time for the demo, and I have to leave Nilusha time to talk about his work. Are there any questions at this point?
Vesa here.
Yes, hello.
One thing I'm kind of like wondering is like how much you are thinking about here, like quality of the detection, and how much you are thinking of like scalability and issues like that. So many vehicles, many objects versus like what you can detect and how kind of like accurately.
I would say the scalability is a big question here. That we are kind of we are thinking about scalability so much that it can sometimes kind of hinder the detection performance. Like as I said, the background subtraction, it uses this probabilistic model, and it's able to self-learn in kind of theoretically any environment. And of course, there will be problems with it brought by different shadows, different lighting conditions. Maybe like the sun can be very low and shine the camera, but it is fully scalable and generalizable as it learns on its own. And with this kind of pre-processing by the background subtraction, we can get these kind of nice boxes for all of the images, so that we can move from object detection to image classification, so that when we know what which area is interesting, we can use like these algorithms that are very general. You can have a data set of just images of backpacks, and they have to be just the images. They don't have to be labeled bounding boxes. So you can use this type of simple classification data to achieve this kind of detection. So yeah, in answer, the scalability is something we think about a lot, and there could be algorithms that if we did like local training, we would get much higher accuracy. But this is kind of a scalable option, so we are looking at that.
Okay, thanks.
Yeah, great. Anyone else with something? Discussion questions?
Yes. Do you think that, for example, within a bus environment, we could replace the linear camera with 3 or 4 stationary cameras to give enough angles to the software to detect all the trash and valuables, like in this case with the blue bottle?
Yes. Excellent question. And I would say that for the kind of real implementations, the focus is more on these stationary wide-angle cameras, because we do realize that these linear cameras, these are quite a innovative and innovative step, and kind of a big thing to install, and they have a lot of moving parts, so to speak. So it is something that we have tested, and it definitely brings benefits. But from the kind of installation point of view, and that we can get the research rolling, so to speak, in my opinion, we should use these wide-angle cameras to get the initial installations, and we can observe the real-life conditions. So yes, in my opinion, the installations should, the upcoming installations should be made with these wide-angle cameras, and as you can see, they operate very well as well. There is not a drastic difference in operation, and they are much easier to install for research purposes.
Okay, that's great. Thank you.
Yeah, thanks for the question. Anyone else have something to say? Okay, I'm taking this as a no for now. That I think there will be time in the end for any types of questions. So I think now I can let Nilusha let him present his work, and I think after he's demonstrated his technology. I think we can still have a general round for questions. But yeah, Nilusha, would you like to step in and show us what you've been doing?
Thank you very much, Risto. Hope everyone can hear me. Just give me a second to start up my camera. All right. Hello, everyone. So first of all, does everyone see both the cameras, both me and the vehicle? I hope it's clear. And I also hope that you can hear my voice well. If there are any questions or if something is unclear along the way, you can always free to ask me. All right, I guess we can get right into it. So hello, everyone. I'll be demonstrating my work done with our research vehicle that you can see here at the back. And my model is intended to be used in shared vehicles, where the idea is basically to capture the rear seating compartment of the vehicle or the cabin and sort of capture an image of it and see if there are any trash items or if there are any valuables which have been left behind by the previous passengers. And the motivation behind this, of course, is to make sure that sort of undesirable objects are being removed so that the next passenger can sort of have a pleasant experience in the vehicle. All right, actually, I should say that I had actually planned to have the demonstration outside because then I actually trained all my images and everything outside where there's like natural light, shadows, and everything. But it's quite impossible and unbearable to do it, especially at this time. It's really warm. So I decided to sort of have it indoors. But I have a way around that. So I'll be able to present results from the images I've taken outdoor as well. But we'll get to that as we go on. And so maybe I'll give like a brief description of the model that I use. So it's a convolutional neural network. It's type of convolutional neural network known as VG16. So if you've heard of it, good. But otherwise, I won't go into too much details of it, but it's basically a type of CNN that can be used, customizable applications, machine vision applications such as this. So the CNN was developed in such a way that the final results should be able to generate 1 out of 3 classifications. So either the seat would be empty and clean, which in that case, there was pretty much nothing on the seat or the carpet area. And it could either contain trash or it could contain customer valuables. So those are the 3 classifications that will be there. And just to give like a quick note about the data that I used to train this model. So I used up to 1,200 raw images that I captured. And with a technique called data augmentation, image augmentation, I was sort of able to expand the data set to around 2,050 images of all 3 classes. So the types of valuables in my data set were, like daily customer valuables such as mobile phones, wallets, bags, earphones, keys, and so on. And the trash class was pretty much tested by using different types of cans and bottles, both metal and plastic. All right, and also in terms of the variations that are there in the images, so apart from the actual object being there, there are also other variations when you think of a vehicle that is running on the street. So for example, the front seat position can be changed, and the camera that I have installed right now actually kind of captures the back area of the seat. That is one sort of form of variation. And of course, there's the ambient light from the outside, and also shadows and so on. So right now, the model has been tested in the Ford Focus. But the intuition here is that shared vehicles of a particular company will usually be from the same model, and therefore this particular model could later be fine-tuned into other car models. Like for instance, you won't be able to sort of install this model directly into another vehicle which has, say, a different layout, but it has to be fine-tuned and used thereafter. All right, so that was just a small introduction to whole setup. I I guess we can jump directly into the in-car setup, like the components that I have in the vehicle. So for that, I will just switch the camera so that I will kind of have to it closer to the car. I hope I can give you a pleasant experience with that. Just give me 15 seconds. All right, so I'm going to try to show you what I have going on inside the vehicle right now. So if anything is unclear or if you didn't see anything, please let me know so that I can show you again. So this right here is the reading compartment of the vehicle. And if I just move my camera over here, right here where you can see like a little bit of a flash, this is actually the camera that I'm using to capture the images. It's on the side of the vehicle, on the left side of the vehicle, near the roof handlebar, where you kind of can keep your arm. And that is actually a fish eye lens, which is used to capture the seating area and also the carpet in the rear compartment. And you will also see this weird strip that goes along the length of the vehicle. That is actually a light strip, which was installed for the purpose of capturing images during nighttime. So obviously this is purely for demonstration purposes, but the idea here is that the light sort of acts as a flash device for the camera when it's dark, so that it could actually have a clear image even when it's dark outside. So now maybe we can move that up in the trunk. All right, I hope you can see what's going on over here. So actually there's like a lot going on over here, but I should tell you that this is actually a research in Aalto, and it's not purely dedicated for the anti-crash project. So there's like other research work that's going on with this. So all these components are pretty much there before I started the project, but this little box over here, right here, that is like the new addition. And that pretty much contains the Raspberry Pi module and the circuitry for the lighting. So the inputs into this box are pretty much the USB cable from the camera, and of course the power inputs for both the LED and the Raspberry Pi. So basically the Raspberry Pi will be connected to Wi-Fi, and that is how the images will be transferred to server, where the algorithms will actually be executed. Once again, this is pretty much the only new addition into this whole setup. Oh, the batteries over here and the board were already there. All right. All right, I guess we can jump directly into the actual algorithm, if that's okay. So maybe I'll share my screen so that you can see the web page again. So I also use the same web page that Risa developed to show my results. I hope everyone can see this right now. Oh, just a second. Yeah, it should be visible right about now. So just to save us some time, I actually took the liberty of capturing one of these empty images while just before the demo started, so that I can quickly get through this particular classification. So it actually happens in 2 stages, as you can see over here. Actually, I think I'm going to change my other camera as well. All right, so right now you can see an image that I took, like I said, 5 to 10 minutes before the demo, and the binary classification clearly output a clean image. And earlier I explained that there were 3 classes which it would finally classify it into, and right now it says that okay, it's empty and it has a certainty of 81.71%. So obviously over here, when I take pictures inside this laboratory, I would usually get like higher certainties, mainly because there's not like a lot of variation in light and shadows and so on. But actually in this image, there is actually a shadow of the artificial lights that are hanging up the ceiling. but still it has been predicted as an empty image, which I would say pretty good certainty. And if you actually look at the image a bit closely, you can see that you can see a portion of the front seat from the camera, but that has not actually affected it. So now what I'll do is I'll put some crash up into the vehicle, and we can see how the algorithm deals with that. All right, so I have with me here some cans and some bottles. So I hope you can see it. I have a couple of cans and a bottle from like a couple of days ago. And what I'm doing is I'm going to sort of place this in the rear, like random places in the back seat, and we are going to see how the classification takes place. So I'll just take my bottle itself. All right. Now that I've placed the objects in the car, what I'm going to do is I'm going to capture an image and I'm going to transfer it to the circuit where I will execute the command to classify it. So I'm just logging into the server right now. All right. So like Risa said, if you have the web page on your computer, that I would recommend it as well, so you can easily see the results. All right. All right. So now that the algorithm has been executed, the prediction model has been executed, I'm just going to refresh my page over here. So my results are actually all the way at the end. So let me just scroll right down. All right, still loading. Okay, so as you can see, when there's like a lot of crash items, the model is quite certain that there is crash, which is why like I've sort of rounded this value up to the nearest decimal place, and it gives us the final classification up to a certainty of 100%. Because there are like many, as you can see, there are like many bottles and cans in the vehicle. But maybe what we can observe is how it would change if I sort of change the seating positions a bit, and if I maybe put like one can inside the vehicle, just to see if that would affect the uncertainty in any way. Set it somewhere random. And I guess I can like, just adjust the seat position. So, all right. All right, I guess we could refresh the page now. All right, so in this case, once again, you can see that the certainty is still pretty, and it has clearly specified it as a crash image. However, it might change depending on what you actually place there. Like right now, this can, I guess, would be a bit easier to detect, so maybe that's why it gives a higher classification. Sorry. All right, so before we go on to the final class of valuables, I actually need to point something that would be important in our case. So you can actually make like a small comparison between my algorithm and what Risto has done. So as you can see in the results, I'm not actually detecting where the objects are, or like anything like that. So it's just a matter of determining whether the vehicle contains valuables, or if it contains trash, or if it contains anything inside of it. And so because of that, there aren't any test images in my set where there are both customer belongings and valuables. And my intuition here is that usually I would expect a passenger who is using a vehicle to leave both trash and valuables. It would be kind of rare. So I've kind of kept those two mutually exclusive for now in this development stage of the algorithm. But later on, when we have to determine the cleanliness level, for example, maybe between a scale of 0 and 5, with 0 being really dirty and 5 being really clean. So in that case, we could actually consider those images as well. But right now, these classes are mutually exclusive. So it might not be very interesting to see the results in these conditions. So I actually took the liberty of capturing a few images while the vehicle was outside, so that I can show it to everybody over here. So what I'm going to do is, for the valuables class, I'm going to pick a random image from my test images which contain valuables, and I'm going to sort of use that as input to the model, and maybe we can see how it performs then. So the script pretty much takes a random image from that directory. That's it. So if you could just give me half a second. All right. All right, so it has taken a random image. Maybe we can just refresh the page once more. Okay, so this is right here, a new image. So as you can see, there's a wallet here placed in the backseat of the vehicle, and it has been classified as a valuable. And I actually included this binary classification step as well, because sometimes the algorithm tends to actually detect something, but it may not necessarily, it kind of tends to sort of, get confused between a trash and a valuable, although it actually detects something. So that is why the binary classification is there as well. But ultimately, you can see that the final image has also been classified as a valuable with a good amount of certainty. Maybe we can try one more image. All right. I'll just refresh the page one more time. All right, so in this case, you can actually see that the mobile phone that I placed here on the cup, but still it has been detected with a good amount of certainty, probably because the image is very close to the vehicle. And also in this image, you can see that there's good lighting as well. So that actually helps a lot to make the classification. So if you would like to see some other images that I've taken outdoor in like where there's trash or if it's empty, you can just let me know. And I can skip for those other classes as well. All right, so as you can see, like there have been some pretty good results, but I should say that there have also been like sort of some practical difficulties in obtaining certain data, because especially for the valuable class. So although the uncertainties are pretty good here, in general, when I did testing for like a batch of test images, the uncertainties were usually like the highest, or in fact, the confidence was pretty low for the images containing valuables. So the main reason behind this is because, so when it comes to empty images, I can just sort of run a script and leave the car outside and park it in different spots so that there are different sources of light and shadows every day, and then just run a script so that it takes an image, say every 30 minutes, so that there's like a lot of variety for training. I can do the same thing for trash as well, because I can find some trash lying around. It's not a big problem. But the issue with valuables is that I don't have like a lot of valuables with me, obviously. So what I did was I actually had three workshops. I don't know if that's right word, but the idea was so that people would come and they would place their valuables in random places on the stage, and then I would capture the image, and these images would be used as training data. So the three workshops were to be held in the winter, and like one in the spring and one in the summer, so that there'll be like different lighting and so on. But unfortunately, I could only do one in the winter, where there was not a lot of variation in terms of lighting, or because there was hardly any sunlight and also shadows. And obviously, I had to cancel the other two workshops because of the coronavirus pandemic. But that was kind of like a drawback in like when it came to like training the model. And the other limitations are also sort of, there are some limitations which are included in the technical design report, but just to go through a few of them very briefly. So very similar to Restore's case, if you sort of place, let's say a dark image, say a black color image, like very far from the camera and, maybe on the clip. And if the lighting is also not that good, there won't be a good contrast between the object and the background. So because of that, it would sort of tend to classify it as an empty image because it will not detect what it is. The same happens sometimes for objects with reflective surfaces. Like here in this image on the screen, as you can see, it's actually a reflective phone, but here you can actually see it crop. But sometimes if there's a lot of light coming into the vehicle, and you place one of these objects like in a very bright spot, then once again the camera would not take a very good picture, and the distinction would be not very good. So also another actually quite a significant drawback of the system would be the fact that the seat pockets or like corners where like customers might put their items in the seat pockets, it will actually not be detected because this camera is not able to detect any of those things. And also there are like drawbacks of it's not able to detect spills, for instance, on the stage. It's been trained very specifically right now. Like I said, for trash, I've only used the cans and like different types of bottles and cans, like different materials and so on. So those are just a few limitations, like the main limitations in the algorithm that has been developed up to now. And I guess the next stage would obviously be to sort of having like I would recommend a better camera installation in the vehicle, in actual shared vehicles, so that we get data which would not be, I would say, biased in a way, because right now I just simply say items. But it would be better to sort of obtain actual images of like crash and valuables while the vehicle is in operation. And that will allow to sort of get all this like natural means of data, and afterwards the model can definitely be fine-tuned to sort of yield better results and yield and sort of identify new data much better. And apart from that, I guess from the data set that I have right now, I've made it available as well. If there's anyone who would like to see the types of images that I have, I would say the results have been pretty nice with like drawbacks, but definitely it could still be improved. But yeah, if anyone wants to see more images like of like the outside, I have like more images of crash and also like images that I've taken outside with like shadows and so on. I could always like execute the script and show you the results. It will also be available later on in the report, but that is pretty much everything I have to say about the model. Any questions are welcome. Thank you. Does anyone have any questions?
Nilusha, maybe I'll ask if no one else. Thanks for a very good presentation. So you put quite many trash there, and then you get like likelihood of 100%. If you put in your demo, if you put like only small tiny trash, will you get the same 100% likelihood if it's being detected?
Actually, it would decrease if there's like a lot of shadows vehicle, because that kind of affects the final result. But in general, over here, since there's not a lot of light, it will easily sort of classify and tell you that, okay, definitely crash. And out of all three classes, crash was actually the most accurate class, I would say. If empty class would sometimes have some abnormalities where even if you don't put anything inside and there's like a very bad shadow falling on the seat of the vehicle, you would still make like a very abnormal classification. Maybe it will say that it's a valuable or even a trash object. It's quite unpredictable. But in general, the accuracy is pretty good as long as the lighting in the seating area is pretty uniform and there's not a lot of shadows and a lot of just in lighting across the seat. Then you would definitely get like high certainty.
Thank you, Nilus. I also saw from the chat that Enrik would have a question, but his microphone doesn't work. So if he can type it, we can then read it from here. But let's see what is going to happen.
Yep.
Maybe in the meantime I ask if this is both for Nilus and Risto, so kind of like thinking of the objects and so forth. Well, I don't know the project and so forth. Have you been thinking of other things that kind of like clear objects? So if you have spills or things like that you need cleaning up with, or it's kind of like trash in a kind of like very, very kind of like physical item sense, or can there be dirt or kind of like phenomena like that?
Yes, thanks, Vesa. That is an excellent question and very important thing considering the like cleanliness. And I can say that I have been able to successfully detect spills, and I've tested it a couple of times. But there is kind of the practical problem of once you make a spill in the kind of setup you have, it can become quite of permanent. So I have tested this a couple of times with water and with industrial alcohol, making spills in the setup, and they have been successfully detected if they have been large enough or dark enough or like enough different from the floor, basically. But there has been the problem that they have left sometimes these kind of like darker areas, these more like permanent stains in the rubber mat. So yeah, it has been tested a couple of times, has been quite successful, but not demonstrated here, and not yet investigated in great detail because of the practical problem. But yeah, thanks, an excellent question. Nilusha might say something.
Some kind of thinking. What about you, Nilusha?
Yeah, I think I could combine a question with what Enrik had asked, because I think it's more along the same line.
Okay.
He was asking me if like what happens if there's dirt or scratches. So, yeah. So what I would say is that if like right now, if the vehicle is empty and if there's like some kind of dirt that just like dust or something, it would definitely not detect that. But if the camera is able to actually detect the difference between like the normal seat and if there's like a scratch, for instance, then it would probably give good result in the binary classification, where it will maybe say that it contains something, well, like the condition is something abnormal and it's actually clean. But since it would definitely give an unpredictable result when it comes to whether it's trash or valuable. So that I cannot say because I have not tested with those kinds of images yet. It will be very interesting to see how that would work as well. But like Risto said, there are some practical limitations when it comes to testing those kinds of images, which are kind of like more permanent vehicle, I would say. But I definitely haven't tested it with any kind of let's say permanent sort of trash in the vehicle when it comes to like dirt, scratches, or even spills.
Yes, I hope we answered enough detail. Enrik, okay, great. Enrik confirmed that it was a satisfactory answer, and we answered this question. Okay, any other questions to any of us? Right, Nilusha or me? Okay, I'd say it's pretty quiet. So everybody is apparently speechless by the performance of our algorithms. That is very understandable. But yes, if there are no questions, I think we are quite well on time in that case. We are 1 minute past, 2 minutes past the time slot reserved for this demonstration. But in case there are no other questions, I guess I'd like to thank everyone for participation. Thank you very much. It has been great to get to show the results of our work, and we are looking forward to further tests. Thanks everyone for coming and having a look.
And if anyone has any other questions, I will put my email right here in the chat so that you can feel free to ask me, and I will definitely reply to any queries. Thank you so much.
Thank you from my part, and thanks for participating, everyone.
Yeah, thanks.
Yeah, thanks a lot.
Thank you. Bye.
Bye-bye.
Yeah, thank you. Bye-bye.
Thank you. Bye-bye. Bye.